Okay, hi everyone. This video is a calc review for Chem 411 at the University of Oregon, Physical Chemistry 1, Thermodynamics. So let's get started with some of the basics. So a derivative, we're going to be talking about a rate of change at a point. So to think of this sort of graphically, I'm just going to draw a little plot in the corner over here. So if we have a curve, like so, the derivative at, let's say, this point is the tangent line to the curve. Okay, so a few rules that we have, then the power rule. If we have a function f of x is equal to x to the n, then the derivative of that function is nx to the n minus 1. Then we have the chain rule, where if we have a composite function, f of g of x, the derivative of that function is going to be f prime of g of x times g prime of x. Those are really the only important rules for this class. I guess there is one more, exponents. So if you have e to the x, or e to the u, I should say, d dx of e to the u is equal to u prime e to the u. So in the case of e to the x, the derivative of that would be e to the x. All right, let's see an example of this worked out. All right, example 1, we have f of x is equal to x to the third plus 2. So let's take this nice and slow with using the power rule. So the power rule says that the derivative of x to the n is nx to the n minus 1. So it's going to be 3x to the 2. But the derivative of a constant is always 0. So I'm going to write this right over here in red. d dx of c is equal to 0. Okay, great. Let's actually see another example. So let's let g of x be equal to 3 over x plus 4 to the 6th. Let's write this a different way, though. X plus 4 to the minus 6. This is actually going to help with rewriting in terms of the power rule then. Okay, let's do this. G prime of x is equal to 3 times the minus 6 times x plus 4. We're going to subtract 1 by the power rule, so minus 7. And this is going to give us negative 18 over x plus 4 to the 7th. Great. So I think that's as much single variable calculus that we need to go over. So let's introduce another definition. So say we have a function. Z is equal to f of xy. So we have 3 variables in this case. So the partial derivatives are defined as follows. Because we can't take a derivative of more than one variable, we have to hold other variables constant. So I'm going to write this in a different color here. So for this function z is equal to f of x, y, we have, this is called del or partial. So partial z over partial x. This means we're going to hold the y constant. Del z over del y, holding the x constant. So this thing right here is called del, and this is what's constant in this situation. Another way to write this that can sometimes be seen in Calc 3 or something like that would be Fy and Fx. Okay, so let's actually do an example right away then. All right. Example 3. So suppose we have a function z is equal to x to the third plus y. Okay, so let's find the partial derivatives for this. So let's consider partial z over partial x holding y constant. So in this scenario, y is the constant. So you could treat it almost in a really simple scenario. Treat like any number, if that helps you visualize it more. So like z is equal to x cubed plus 2. So if y is constant, then partial z partial x holding y constant is just going to be 3x squared, because that y is a constant, and a derivative of a constant is 0. And then we have partial z partial y holding x constant. Since the x term is constant, we can call that a number if we wanted to. And the derivative of y is 1. Okay, let's see one more example. So let's say that, let's go with z is equal to w plus x times y. So we have 4 variables in this scenario. So partial z, partial w, holding x and y constant. So if x and y are constant, we can just give the same treatment as before, and the derivative of w then is 1. Partial z, partial x, holding w and y constant. W is constant, we can treat that like a number. Y is constant, we could do the same thing. So the derivative of w is 0. The derivative of xy then is what? Yes, y. Because y is constant, you can call it like a 2 if you wanted to. And finally, partial z, partial y, holding w and x constant. So the derivative of a constant is 0. The derivative of this then is going to be x. Okay, let us actually do one more example. And I'm going to try and give you some time to do this one on your own. So let's say z is equal to x squared y. So pause the video if you need to take a little break. Go fill up your water bottle or something, get a snack, think about the joys of calculus, something like that. All right, you should be back now. Great. 2 scenarios, partial z, partial x, holding y constant. So if y is a constant, we're taking the derivative of x, we're going to have 2xy. Partial z over partial y holding x constant. The derivative of y is 1 then, so we're left with x squared. All right, excellent. Now, let's actually pull this back a bit to thermodynamics. So we want to consider some sort of scenario then with an equation that we'd have in thermodynamics that we're taking a derivative of then. So let us actually consider the Virial equations. So one of the Virial equations is z is equal to, apparently my pen is dying, z is equal to 1 plus b over vm plus c over vm squared, blah, blah, blah. Okay, great. So vm in this case, because I know that's a bit of a different notation, vm is the molar volume. It's just another way to write it. Because the bars get a little messy with the fractions. So let us actually do this then. We're going to take dz d1 over vm. So then the derivative of this is going to be 1 plus b plus 2c over vm dot dot dot. So what happens as vm approaches infinity? Oh, sorry, that is a 0. The derivative constant is 0. So as vm approaches infinity, the only term that was left is b. Okay, so you're probably curious to see a few more sort of examples. So let's actually continue with the Virial equations. So still using the same Virial equation, we're just going to approximate it to be this. Now, what if I wanted to find dz dt at constant Vm, molar volume? So we would write this as partial z, partial t at constant Vm. Now this might seem a bit tricky because you think, okay, this whole term is going to be 0 because temperature isn't in there. Well, temperature is in there. So the virial coefficients are temperature dependent. So that means we need to basically treat z as follows. Right? Okay. So here's what we're going to do. Oh, you should be so excited because I know I am. Okay. Partial z, partial t, holding Vm constant. Of course, the first term is going to be 0 then. And then we have, what do we do with this? So we're going to have to use a slightly different method of going about this if we want to consider it. So what we're going to have to do is just write b prime of t Vm. and because we know that it's a function of t. Otherwise, we wouldn't be able to, or that term would just go to 0. So I want you to think about that for a second and just make sure that you know what variables are being held constant, which ones are actually a constant. Because this is a constant, but it still has a temperature dependence. Okay, great. So we thought about that a little bit longer, and just basically remember that that is temperature dependent. So just watch out for that. Now, if we wanted to do something a little more complex with the virial equations, and we wanted to actually take things a step further and have our PVM over RT is equal to this, and we wanted to find some sort of derivative with respect to temperature, we'd have to be a little more careful. So I'm moving all the terms back over here. So we'd have to be more careful with this scenario now, because we have temperature, again, here and here. So if we wanted to consider del P over del T at constant molar volume, we'd have a chain rule case, or sorry, a product rule case. And we have to be careful with this, again, making sure we remember that it's a function of t, because I wrote it there. But you'll never see this actually written as a function of t, you'll just see it written as b. But I'm just saying that to illustrate a point. So, the derivative of the first times the normal second. So we have r by Vm times 1 plus b of t over Vm plus the regular first times the derivative of the second, that's 0, and that's going to be b prime of t over Vm. So just watching for some subtleties when you're doing a problem like this is always a good thing to remember. Okay, so we're going to end on one final note then. Draw the line here. So the van der Waals equation is defined as follows. P is equal to RT divided by V minus B, we're going to call that the molar volume, minus A over Vm squared. So the reason why this came about, so we have, well, the ideal gases, we needed something to account for collisions and forces. We have the high pressure scenario, small volume. So this term accounts for the collisions forces and the pressure. Whereas, I'm going to use a different color, this term accounts for the volume. It's a bit more clear when it's written in a different form, which I will write in just a second. We're going to write it in red right over here. So we can rearrange this as P plus A by Vm squared. And we can multiply over the Vm minus B and set that equal to our RT. So that's sort of the equation that we're used to, and we can see that if we cancel those terms out, we're left with the ideal gas law. So this could be sort of talked about as the pressure correction. And this is the volume correction. So hopefully that made you think a bit more about why the van der Waals equation is the way it is. So we're going to talk about one last thing then. Is, for fun, I'm not going to do it in this video, but usually the first and second derivatives are used in some calculations. So del P del Vm holding T constant is equal to 0 under very specific conditions. So these conditions are true at the critical point. And at the critical point, we have these lovely, lovely things called critical constants. We have VC, TC, PC, ZC. And at the critical point, we can calculate these critical constants pretty easily because of this condition. So why are these two conditions true at the critical point? Take a look at the graph of P versus the molar volume, and you'll be able to see why those are true at the critical point. So just to recap then, so you should know a little bit about what a derivative is. So if we slide back to the first page, it's a rate of change at a point. We went over some rules, some examples, the definition of a partial derivative. We went over a few examples. We talked about the Virial Equations, what happens at a certain point for those. And we also went in a little more depth with the Virial Equations and said, hey, this becomes a little more complex. And then talked about the van der Waals equation at the end. So again, if you have any questions, feel free to let me know. Post it in the comments. Send me an email. All that good stuff. I guess don't forget to be awesome. Have a great day. Thanks for watching.